Hello everybody, my name is Mikolaj Pawlikowski and I would like to thank you for coming to this talk. I'm going to talk to you about something that really excites me. I'm going to talk about chaos engineering and in particular how it overlaps with SREs and why SREs really should love chaos engineering to begin with. Here's the plan for the next half an hour or so. Like any good scientist, we're going to start with defining our terms. We're going to see what SRE is. We're going to see what chaos engineering is. And then we're going to focus on the actual overlap where the two come together to create an extra value. I'm also going to use this opportunity to talk about my latest book, Chaos Engineering Crash Test Your Applications. And I'm going to finish with two demos to kind of illustrate what I really mean and kind of show you in practice where chaos engineering can really help the SREs. Sounds like a plan? Well, hopefully. So let's start with SRE, the Site Reliability Engineering. I'm pretty sure that some of you at least are familiar with that. It's a concept, a term that was coined at Google. And in one sentence, it's basically what you end up with if you give the operations work to software engineers, right? So the way that I like to think about it is that, if you on a Friday evening go to an SRE pub, assuming that kind of place exists, imagine what you're going to hear about, You're probably going to hear things like reliability, like performance, like latency, like availability. You might hear someone in the corner, ranting about on-call and alerting and monitoring. You're probably going to hear someone, talking about business objectives and SLOs and SLAs and stuff like that. You might even hear someone, mention latency. And that's all good. That's basically what it gives you a good idea of what these people actually care about. If this is what we talk about on Friday evening, that means that they must deeply care about. And this is, kind of like the kernel of what SRE really is. These are people who deeply care about making sure that things run smoothly, right? So it's one thing to kind of write software and features, and it's kind of like a different problem to actually run that and run it well and at scale and without hiccups, right? And this is where we get to the core of what SRE is, right? So all these things that I mentioned in the virtual pub, they all kind of have to do with reliability. Reliability is kind of this like encompassing term that is a little bit vague and kind of can involve pretty much all of those words here, right? So it might be that your system is performance-based. It might be that, for example, the value that your system provides depends on how many operations per second it can produce. In which case, the reliability will be to make sure that that performance can be sustained and that it can be sustained long term. Or it might be that it's much more important for a system to be highly available. Because if users can't use it for even a small fraction of time, they're going to be much more upset than if the performance is degraded. So that might be your reality of reliability. It might be latency. It might be that people are browsing funny videos and they really care about latency, and if the video is too slow, and they're going to go and spend their money elsewhere or watch the funny videos elsewhere. So that latency, you can measure that, and this is your reality of reliability to make sure that that latency is maintained, right? Then you have all the monitoring, alerting, on call. These are the things, these are the tools that show us the visibility, give us this visibility into what's actually going on under the hood in the systems, and alert us when our attention is needed. The dreaded on-call and the paging where people sometimes have to wake up to fix something, these are the people who do that. These are the people who set up the alerting and set up the monitoring so that they know that something's wrong, right? The capacity planning, that is also part of your reliability. It's not the most glamorous, hardly anyone likes to talk about a massive Excel file when they try to predict how much resources they need, but it's essential. Someone needs to do that. Someone needs to think, okay, if we're going to grow by this many users in the next quarter, we're going to need more disks and more CPUs and more RAM and more X and Y, right? This is part of the reliability. Or the SLOs, right? Probably heard of the SLAs. You might not have heard of SLIs and SLOs. SLI stands for Service Level Indicator. And it can be any quantity that's measurable that you care about in terms of verifying that your system runs well. So let's say that, for example, you run some kind of API. It's an API where people can send a request and they get the right meme, right? Your meme API. And the SLI that you might care about is, for example, the speed of the response. Let's say that the 99th percentile of the response time is something that you care about, right? With that, you can create, design an SLO, which is an objective, a service level objective, which is basically a range of a particular SLI that you care about. Like, the mentioned 99th percentile of response time, you might want it to stay within 100 and 200 milliseconds, for example. Right? So that's an objective. And then SLA is an agreement. It's basically a contract between two parties when one of the parties provides some kind of service and they promise that this SLO is going to be satisfied or else. And, typically the or else is some kind of financial compensation or something like that. It can be a cool t-shirt, it can be anything really. But the idea is that, we're going to do whatever we can to make sure that that SLO is satisfied. And if it's not, we're going to make it up to you somehow, right? So this really is a kind of, an example, a sample of what the SRE is. And, some of you will be like, okay, well, that kind of sounds like operations. And yeah, bingo, that's basically what it is. It's the operations just with more software engineering to it, right? The software engineering being used to remove the bad bits, to try to kind of automate the bad bits away. And the bad bits have a really funky name, a nice name of toil, right? We typically speak about toil when we talk about SRE. So the deal for the SREs is that they're going to spend less of their time dealing with the actual operations, the on-call, the crisis management, and spend most of their time using their software engineering skills to roll out automation, to automate the toil away out of the equation, right? So they're going to write software to automate things, so that there is less ops and on-call to do to begin with, right? And that's it. There is a lot of hype about that, but at the core of it, this is what it is. A lot of the systems are pretty big and pretty amazing and pretty everything, but you don't have to be at Google to be an SRE, and there are plenty of systems that need the same kind of treatment to verify that it runs smooth as silk, right? Okay, so kind of define the SRE. What about chaos engineering? I'm guessing that some of you probably first came into contact with chaos engineering in the context of Chaos Monkey, and that's great. That's fantastic. But it also kind of gives chaos engineering the bad rep. Like if you Google that, Chaos Monkey was randomly taking down VMs for Netflix so that they can detect things that they didn't detect with other testing techniques. But if you Google that, you're probably going to end up with something along the lines, let's break things in production and, breaking things on purpose. And that's great, but the kind of breaking things is not really what we're after here. What we're after is experimenting to verify hypotheses about our system's behavior in the presence of failure. So yes, we want to inject the kind of failure, introduce the kind of failure that we reasonably expect to happen, but we don't really, try to break the system. We actually try to learn that either the system behaves the way that we expect, that's the hypothesis, or deny that and learn that it needs to be fixed. Okay, so at the core of it is much more scientific than just going and randomly smashing things in production. We actually want to very finely control the amount of failure and the type of failure that we inject most of the time to verify that what we think is going to happen is actually happening, right? That we are right thinking about properties of the system. And this is really where the value comes from. And sure, there is the aspect of kind of like, on the verge of chaos engineering and fuzzing techniques, where you want to create this kind of like half-random, pseudo-random situations where you can end up with, combinations that you didn't think about yourself to test out. But this is just a part of it, right? So next time you see that it's, let's randomly crash things in production, that's not really what it is about. And at least it's not really what it's about for everybody. If this is a good idea for you, if your production system is of a nature that allows you to do things like that, that's great. That's absolutely stunning. If you are at the maturity level where you can actually run this kind of thing in production, that's great. Because if you think about that, you can never really 100% test anything before it hits production, right? Because you can try very hard to reproduce the kind of failure that you expect. You can try very hard to reproduce the same environment in some kind of test stage, dev stage, pre-production stage. But at the end of the day, there will be things that will be different. It might vary very, very slightly. It might just be like a user pattern, but it's technically either impossible or prohibitively expensive to actually do something like that. Right? So if you can, this is like the holy grail when you run this kind of things in production, and you can verify and uncover real problem on a real production system. But it also gives it bad rep because, when people read about that, they stop taking it seriously. It's like, well, yeah, okay, cool. We would never do it here. So just kind of want to, remind you that this is the case. So now we have these two concepts. We have the SRE on the left-hand side, and we have the chaos engineering on the right-hand side. And I would like to argue and spend the rest of this time that we have together now to kind of show to you that where the real magic happens, where the love happens, is when you start using chaos engineering for your SRE purposes. Okay? And I'm not just saying that, I deeply believe that. In fact, I believe so deeply into in that I wrote a book about it. It's called Chaos Engineering, Crash Test Your Applications. It's available right now in the early access from Money. If you go to money.com/books/chaos engineering, and it's trying to show you that you don't need a massive distributed system. And if you have one, that's great. But you can apply this chaos engineering techniques to pretty much any system. It can be as simple as a single process running in a single computer. I have a chapter there that shows you how you can treat that single process and that single computer as a system and verify things like, for example, block some system calls and verify that actually this process as a system might not behave the way that you expect it to behave. It might not have the error handling or the retries that you expected it to have. It might actually work differently. And that kind of builds up from the small examples, looks into how to introduce failures between components, how to introduce slowness in between components at like the networking level. It talks about introducing failure through modifying code on the fly. If you happen to be running something that executes in a JVM, there's a chapter pardon, where you can learn how to inject bytecode into your classes without actually modifying the source code. So you can take someone else's code and inject the type of failure that you expect, and then verify that the system behaves as a whole in that manner that you expected. And then it goes all the way, builds up all the way to things like Docker, where you test out things running Docker, or you test out Docker itself, and Kubernetes if you have larger systems that are running there distributed, and kind of anything in between. Or even if you want to test, chaos engineering test the kind of failure that you expect in your front-end JavaScript. It's really a great tool. And I'm really wanting to show people that this is something that you can use in many situations. And it's not just for Netflix and for Google. This is much more broad than that. Okay, so these are the things that we just discussed. And as you can see, apart from snarky t-shirts that don't really need an improvement, typically SREs have them on point. All of these things can be helped with the use of chaos engineering. All of these things can be designed experiments on and can be verified through these experiments, verified in terms of hypotheses and assumptions that we have about these things. Okay, so just to show you, the overlap is big. I kind of felt like the previous slide was showing the overlap as a little bit tiny, so I kind of zoomed in here. And I would like to now show you a little bit more in practice what I actually mean about when I say that the chaos engineering can be leveraged for SRE. So let's jump to my first demo. What you're seeing here is the VM that comes with my book. It's more or less vanilla Ubuntu with all the things that you need for chaos engineering pre-installed here. I'm going to use one of the examples that I have here. This is coming from a chapter on Docker, and it's a descriptor for Docker Swarm or Docker Stack that describes two services. One of them is called Ghost, and it basically just runs the image for Ghost and then provides some configuration for the database and the database itself, which is MySQL 5.7 with not a particularly safe password. So the thing that what it does is basically start these two containers with the configuration to point at each other so that we can run Ghost. And if you take a look, I actually already have it running. I already ran the Docker stack, and you can see my Ghost container and you can see my MySQL container. If you're not familiar with Ghost, it's a blogging engine. It's a little bit like WordPress, but just a little bit more modern. Also note that the names of the containers, one of them starts with Meower Ghost and the other starts with MeowerDB, because we're going to use these names later on. So first thing we should do is actually verify that this thing is working. So we should be able to go to 127.0.0 to port 8080, and we should be seeing the application. And boom, looks like it's actually working. Okay, so this is great. We get something, but what we actually care about is some kind of SLI, some kind of metric that we care about and we want to make sure that we satisfy, because that's how we do as SREs. Okay, so one of the most basic things that we can do is use something like Apache Benchmark to basically create a lot of requests and verify how quickly this request return. So this is just running AB with 10 seconds and concurrency of 1 to the 127.0.0.1 8080, so that we get an idea. So you can see that during this 10 seconds, we got 105 requests that were complete, and we got no failed requests, which is also great, which translates into 95 milliseconds per request, which is, let's be honest here, running on localhost, not the record of the world, but it's not too bad either. Okay, so this thing, what we just did in the chaos engineering parlance, would be called steady state. This is what the metric that we have, which is time per request, and SLI of time per request is roughly 95. If we run it again, we're probably going to get slightly different number, but I would expect that this is not going to be very different because we didn't change anything. Okay, so let's just finish the 10 seconds. Actually, now it's 50 milliseconds. I guess it was warming up a little bit, in which case I'm going to run it again so that we can actually verify that the steady state is okay. 10 seconds is not particularly long, so it looks like there was some cache warm up, and now we have about 50 milliseconds time per request. Brilliant. All right, so it would be a shame now if someone went ahead and introduced some failure, right? So we have two components. We have the database and the engine, the blogging engine. And what we might want to do is just see what happens if we introduce some slowness, some delay between the two at runtime, right? And as it turns out, it's actually pretty simple. We can do it pretty easily. One of the things that make it easy is this tool called Pumbaa. It's an open source resilience tool that essentially, apart from doing things like killing containers, wraps up TC, traffic control Linux utility, in a really, really cool way. So I'm not gonna go too much into the detail, but I just wanted to know that what you can do is you can ask Pumbaa to actually run the TC from inside of a container that's attached to the container that you care about to introduce slowness. So what we want to do is we want to introduce slowness on this container, and we're going to go ahead and actually introduce that to all the networking. And with Pumbaa, that's pretty simple actually. I already have a command here that I use, but I use this netem subcommand. We're going to run it for 120 seconds, the entire experiment. We're going to specify a TC image because Pumbaa allows you to either rely on TC being available in that container that you're targeting, or if you're using someone else's container or you just don't want to have TC there, you can start another container like I just described, like for example this one that has TC built in to connect to that other container and execute TC in there. And then we're going to add a delay, time delay of 100 milliseconds. And we're going to ignore jitter and correlation for now, both set to 0, so that we can just see the results more easily. And then the nice feature is that you can specify here the container name, or if you prepend it with RE2 : you can use regular expression. So for example, my meower_db is going to match everything that starts with it or includes that. So in particular, the name of meowerdb that we were looking at before, the one here, is going to be matched. All right, so I'm going to go ahead and run it. And what it should do is start that other container, execute the stuff, and end. So I'm going to start another tab so that we can see what's going on. And the funny thing is, an interesting thing is that you'll see the actual container being created and exiting 19 seconds ago. And that container executes DC. And when this command is done, it's actually going to go ahead and execute another container that's also going to be visible here. So I'm going to go ahead and I'm going to rerun the same AB on port 8080 to verify our state right now with the 100 milliseconds added. And boom, look, we went from 50 milliseconds roughly to a 500 milliseconds. So from roughly 200 requests in 10 seconds to just 18. So what happened here, right? You could have expected, we can also verify that, rerun that just to make sure that, you know, we get consistent results. But what happened is that you might have expected the 100 milliseconds in between the database and the ghost container to translate into an extra 100 milliseconds of delay to the user. But what actually happened is that we got almost 500 milliseconds of delay. So we got a multiple of that. And the reason for that is that Ghost probably talks to the database more than once, even for the the index page that we're querying. And that means that if that container's networking is slowed down by 100 milliseconds, what we're actually going to see is closer to 500 milliseconds delay. So just to confirm here, I'm going to rerun it again so that we can see that we're back to 50 milliseconds because the Pumbaa setup is done. So about 60 milliseconds, which is good enough. And then if you look at the Docker ps-a, you can see that we have the other one, which the first one was tc qdisk add, and then the next one was tc qdisk delete that exited 39 seconds ago. Okay, so this is how Pumbaa was able to actually affect the networking of the container that was running an image that we didn't instrument in any way. So this is like a really very short version of this demo, but my goal here was to just kind of show you how easy it can be with the right tooling and the right knowledge to verify things like that. And now we know that if we can expect reasonably the database networking to have delays like 100 milliseconds, that will affect our overall delay for the Ghost setup by much more than 100 milliseconds, and in particular by something closer to 500 milliseconds. So if the delay rose to a second, we could probably expect to actually see something closer to 5 seconds rather than just 1. Okay, and this is my second demo where I would like to show you a little bit more on the Kubernetes side of things for all the people who are using Kubernetes to deploy their software. So let's take a quick look at SLOs on Kubernetes. The purpose of the second demo is to show you how useful chaos engineering can be for SREs to verify their SLOs and to detect breaches in their SLOs. So I've got here a Minikube setup, just a basic one with a single master here, and I've got a bunch of pods running. Also nothing out of extraordinary. This is just the stuff that Minikube starts with. And what I'm going to do is I'm going to use a tool called Powerful Seal. It's something that I wrote a while back, and it's a tool for chaos engineering for Kubernetes specifically. If you've not used this before, I would recommend going to GitHub and giving it a try. But basically what it does is that it allows you to write this YAML descriptions of scenarios. And then for each of the scenarios, you can configure a bunch of things that it can do to verify that your assumptions are correct. And if they're not correct, it's going to error, and you can alert on that. So if you want to get started with that, there's a get started quick little tutorial, but the kind of most important stuff is about writing policies in this section here, where you can see the different examples of the different policies that you can see that you can implement using Powerful Seal. And if you are wondering what the syntax looks like, there is an up-to-date automatically generated documentation that shows you what kind of things you can do. So if you do scenarios, steps, then you can see the kind of things that are available to you. So probe HTTP, kubectl, pod action, node action, wait, and stuff like that. But this is for another day. I just wanted to kind of give you a quick insight into where to look for those kind of things. But let's take a look at what it actually looks like in action. So back to our little Minikube setup, I have a seal already available here that I pre-installed. And I also prepared two little examples of a policy. So I'm going to start with the hello world, and this is what it looks like. It's a simple YAML with a single scenario called count pods not in the running state. And what it does is that it has a single step with pod action. And inside of the pod action, there's always three things that you can do. You match a certain initial set of pods. You can filter them by whatever property or whatever filters that you feel like. So in our case, I'm going to match all the pods from all the namespaces, and then I'm going to pick the ones that have the state property that is negative, not running. And then I'm going to count them, and I'm going to verify that the count is always 0. So what it's going to do for me, we saw the get pods, all of them were running. So this kind of verification, very simplistic here, shows how you can kind of continuously verify that the assumption that you make, the assumption being all pods are running, is actually true. And you can do that with the 20 lines of YAML. So in order to run this, we're just going to do seal autonomous to invoke the autonomous mode, and then we need to specify the policy file. And this is simply done by the policy file flag. And if we run that, Powerful Seal is going to connect to our cluster, and what you can see here is that it matched the namespace star, so it matched all the namespaces, matched 11 pods in that, corresponding to the pods that we found here. And it found an empty set after the running negative true. So the filtered set length is 0, and the scenario finished successfully. By default, it's also going to go ahead and sleep for some time and retry that later on, which is also configurable. So if we just wanted to verify that this is actually working, what we could do is remove the negative and verify that it's failing if we try to count the running state and the checkpoint, the count is not 0. So if we run it now, this should fail, complaining that we got 11 pods instead of 0, which is exactly what we saw here. And you can configure Powerful Seal to either fail quickly if this happens, or if you want this kind of ongoing stuff, it can produce metrics that you can later scrape. So with just a few lines of YAML, we're able to verify an SLO, which is kind of silly, all pods running, but gives you an example of what you can do with this kind of thing. So let's do another example, a little bit more complex than that. I prepared another one called Policy 1 for you here, and let's take a look. So this time we actually specified the run strategy. So we want to just run it once. We got an exit strategy, fail fast. And the scenario is a little bit more complex this time. So what I'm trying to verify here is that the deployment SLO is that after a new deployment and a service are scheduled, it can be called within 30 seconds. So let's say that I designed my Kubernetes setup and I designed all of the bricks in a way that I am fairly confident that at any given time, when I schedule a new deployment and a corresponding service, within 30 seconds, everything will be up and running, and I'll be able to actually call it. So the way that I implement that is through the kubectl action. Kubectl action lets you more or less specify the payload and the action, so apply or delete. It's an equivalent to kubectl apply-f of the standard input. It also allows you to automatically delete at the end, so that you can clean up and so that you don't leave some kind of artifact after you're done with that. So the payload here is a little bit more complex. It's actually deploying another application that I wrote that is very useful for Kubernetes. It's called Goldpinger. And Goldpinger allows you to basically deploy an instance of a Goldpinger per node by using a daemon set, typically, or you can deploy it more or less whenever you like, whichever way you like. But the default use case is that you use a daemon set so that you run an instance of Goldpinger per node, and then they continuously create this full graph of connectivity between the nodes that you can use to verify whether there is any issues connecting, on whether your networking is slower between certain nodes and stuff like that. So this is like a drop-in that you can run on your cluster, and you can verify this kind of things. It also produces metrics and things like heat maps and stuff like that. But going back to our example, in order for that to work, it needs a service account so that it can list pods, so that every Goldpinger instance can actually see what other Goldpinger instances are there to send pings to. And then we've got the deployment, and the deployment is fairly standard. Right now, I only have a single node, so I'm just going to deploy a single replica. It has a selector, it uses a service account that we just set up, and a bunch of variables here that are not particularly relevant to us right now. This is just to make sure that things working. It also comes with a liveness probe and readiness probe, so that we know that it's only if we can ping it, that means that it was able to verify the probe initially. And finally, we've got a Goldpinger service, a service that we're going to use to actually issue a request. And then after that, this is where our SLO kicks in. We verify that after 30 seconds, we expect that. So the magic number here, our magic range is between 0 and 30 seconds. And finally, this is where the verification happens. We have an HTTP probe that calls the healthy endpoint of the Goldfinger service in the default namespace, which is the one that we defined just here. So all in all, what it's going to do, it's going to go create the thing, wait 30 seconds, and then issue the HTTP request to verify that it gets a response on the particular port. Okay, so with that, we can go ahead, and this time instead of hello world, we're just going to run the policy one. But before we do that, actually, just to show you, we're going to do get pods-aw in the background, so that we get all the new pods that come up and all the pods that are being terminated, so that it's actually visible to you too. So again, our seal, and we have the policy one.yaml. I'm just going to go ahead and run it. So it starts, it read the scenario. You can see that it created the deployment, and here our kubectl in the background is actually displaying the new pod that is already running after 4 seconds. And now we've got about 25 seconds to wait. So, if there was some kind of elevator music, that would be good. It's running for 25 seconds, so we're not that far off. And then making a call. Powerful seal tried to make the call. It got a response. You can see the response generated by a Goldfinger. Scenario finished. Cleanup started. As you can see, that's the thing that I was describing before, the auto delete. It deletes all the things, the pod gets terminated, and Powerful seal carries on. So if we list our pods again, we can see that it's actually terminated already, the Goldfinger. And if you run this continuously, you'll be able to verify that your SLO of 30 seconds for a new pod coming up is actually being satisfied or not, depending on what's going on. So I don't want it to be too deep of a dive, but if you if you want to dive deeper, that's absolutely great. I would recommend going to the Powerful seal documentation back in the browser here, and just at least go through the different examples here. We have like the new pod startup, we got the pod reschedule, where we actually go ahead and we kill a pod, and then we wait a certain amount of time, and then we verify that the pod is running. Powerful seal can also integrate with cloud providers, so things like AWS, Azure, OpenStack, Google Cloud. There are drivers for that, so you can say things like node action, like this. You can say, for example, pick all the masters, pick the masters that are up, and take a random sample of size 1 to just take a single master that is up and stop that thing. And then we can verify that, things continue working the way that we want it. And if you want, you can put them back up explicitly like that, or there's also in the stop action, you can do auto restart, etc., etc. And that's all I had for you today. Once again, go grab my book. If you want to reach out, there's my contact details that are available there. If you have any questions, I'm happy to chat. And hopefully, I'm going to just leave you with this new tool that you can use. And if you are an SRE, you should be using it. If you're not an SRE and you would like to become one, this is something that's going to help you with that. Thank you very much, and see you next time.